Bounded sequences. So we say that a sequence is bounded if its absolute value cannot exceed some given constant real number. So the definition would be the following one. We say that a sequence of real numbers is bounded if there exists some positive number, say m, m is a real number, such that the absolute value of each element in the sequence is not bigger than m. We could say smaller or equal to m. And we could also say that m is an upper bound to this absolute value of this, to the sequence of the absolute values. And the boundedness notion is very important in sequences because we're going to prove that every convergent sequence has to be bounded. So let's see how do we proceed from here. So equivalently, if we say that a sequence is bounded, this means that there exists some symmetric open interval around the point, in the case of real numbers, it's around 0. So it's a symmetric interval around 0, and this interval contains all the elements of the sequence. Okay, so yeah, we could have m strictly bigger or closed interval, it doesn't matter. The important thing that, or we could slightly increase m, but the important thing that there exists this open interval that contains all the elements of the sequence. This is what it means for a sequence to be bounded. Okay, so for example, if we look at the sequence from previous examples, then this sequence is entirely contained in this interval from -2 to 2. And if we plot this, then this is what we see. So we plot the elements of the sequence on the x-axis. And so we see that the elements are really dense around the limit, which is 0.6. And since the sequence is convergent, we'll prove it has to be bounded. So in fact, it is contained entirely in this interval, symmetric interval, from -2 to 2. All the elements are in here. And if we make an analogy here, so the only thing that we really need is that we have this notion of a distance, right? Because this interval from -2 to 2, we could say that it's an open ball with radius 2, but on the real numbers. And when we say an open ball, what we mean is the set of all the points whose distance from 0 is not greater than 2. Okay, so I started saying this, so let us reformulate this indeed for this metric. So this function dxy is how we measure distances on the real line, and therefore, if we reformulate this, then what it means for a sequence to be bounded is that there exists some real number, positive real number r, and I call it r for radius, but nothing really significant. It could be this m that we've seen previously. And so such that, so the distance of an from 0 is actually the absolute value of a. And so we see that the distance of an from 0 is not greater than r, and it's back to this notion that all the elements of the sequence are contained in this ball of radius r. In this case, this ball is just this interval, symmetric interval from -r to r. And so this is our open ball. So, and boundedness, it's not important for boundedness, particularly that this point is 0. Because if it is bounded with respect to this origin point, then it is bounded with respect to any other point. And so indeed, what I would say here, if it is contained in this, if the sequence is entirely contained in this ball of radius r around 0, and remember it's just this open interval from -r to r, at least when we are talking over the reals, then it will be also contained in some ball, perhaps with a bigger radius if we shift it, but around this other point x0. So let's prove this, right? So suppose that the distance of all the sequence element from x0, let us compute what is this, right? It is smaller or equal by the triangle inequality from the distance from an to 0 plus the distance from 0 to x. That's the triangle inequality. And we said that for all the elements of the sequence, we have that this is no more than this fixed radius r. And this is just a number, right? So if we denote by r prime this number, then we also see that for each an, the distance of an from x0 is no more than this constant number r prime. So which shows that if this sequence an is contained in this open ball of radius r, then it's also contained in this open ball around the point x0, not necessarily 0, but with this bigger radius r prime. So if it's contained in a ball centered at the origin, then it's also contained in some ball with finite radius around any other point. So if we want to generalize the notion of boundedness to metric spaces, then we would say that a sequence or a set is bounded if it's contained in some ball that is the collection of all points whose distance from some point is no bigger than a fixed number. So let us now look at this definition. So xd, let xd be a metric space. So we have a way of measuring distances. And so we would say that a subset y of x is bounded if there exists some point and some positive number r, such that this entire set is contained in this ball of with a radius r around the point x0. And for a sequence to be bounded, it means that if we look at the collection of all the elements of the sequence as a set, then this set has to be bounded. And in fact, so here the point with respect to which it is bounded also doesn't really play a role here. It doesn't matter. If it's bounded with respect to one point, it's going to be bounded with respect to another point. And so let's prove this, and the proof goes unchanged from what we've seen on R. So suppose that this set y is contained in this ball of radius r around the point x0. So this means that the distance of every point in the set y from the point x0 is no more than r for every y in y. Okay, so if we define this r prime to be r plus the distance between x and x0, so what we have is, if we use the triangle inequality, and now let us consider the distance from y to x, okay? And so again, invoking the triangle inequality, we have that this is no more than the distance from y to x0 and the distance from x0 to x. Now the distance from y to x0 is no more than r. That's what we assume, that every point is contained in this ball. So if this too abstract this notion of a metric space, just think of this ball as this interval from minus r to r, or around x0. So it's an open interval with radius r around x0 if it's too abstract. But in any metric space, this is just a collection of all the points whose distance from x0 is no more than r. And so using a triangle inequality, so this number is no more than r, and this is just a number. So this is a constant. So call this constant r prime. And then we have that for every point y in y, the distance of y from x is no more than this number r prime, which means that this point is contained in the ball with radius r prime around the point x, not x0. And this means that the entire set y is contained in this ball with radius r prime. So the point with respect to which the set is bounded really doesn't play a role. If a set is bounded with respect to one point, it is bounded with respect to any point. Okay, and so now we have this definition for sequences. So if we look at the collection of all the elements of the sequence as a set, so we say that the sequence is bounded in a metric space if there exists a point such that that the sequence is contained in a ball centered at this point x0 with some positive radius r. So a sequence is bounded if it is contained in some ball. We could even choose this ball to be open ball. So that is, the sequence is bounded if this set as a subset of x is a bounded set of this metric space. So the only thing that we need in order to define the notion of boundedness is the ability to measure distances. Okay. So on the real numbers, we can get more specific because on the real numbers we have order. So we can compare elements. We can say, okay, this number is bigger than this one, and this number is smaller than this one. And this comparison is something that we cannot always have in arbitrary metric space. So let us go into the specifics of real numbers. So here's this, we have this following definition. So we have a sequence of real numbers. So we can define this notion of bounded above. So a sequence is bounded above if there exists a number that is bigger than all the elements of the sequence, right? And this number m is called the upper bound. Similarly, we say that a sequence is bounded from below if there's a number, a fixed constant number, that is smaller than all the elements of the sequence. And we say that the sequence is bounded if it is bounded below and then bounded above. So this is slightly different definition in case of the real numbers, because previously we said that the sequence is bounded if it is contained in some symmetric interval. So let us prove that this definition is exactly equivalent to the previous definition. So let us prove this. So if the boundless definitions are equivalent, so if the sequence is bounded with respect to the first definition, that there exists this number, positive number m, such that an, every element of the sequence, is between m and minus m. M is positive, of course, and this means that we can pick this as the smaller m. We can choose it to be minus m, and then this is the bound from above, and this is the bound from below, and then this the absolute values, and conversely, if we have that a is between those two numbers, then choosing the maximum of those absolute values, we can actually see that the absolute value of every element of the sequence is no more than this number. So this number is just the total bound. So all the elements will be contained in the symmetric interval around 0 with this radius, which is the maximum of those two. So in fact, those two definitions of boundedness, which means below and above, is equivalent. So we had equivalent definition, it has to be bounded above and below, or we could say that all the elements of the sequence are contained in some symmetric interval. This is equivalent. Okay, so now we're going to prove the following theorem, that every convergent sequence of real numbers is bounded. And so it shows that boundedness is a necessary condition for convergence. Okay, so to get the intuition, let us now look at this convergent sequence. So let us plot its limit. So this would be the limit of the sequence, and we see that all the elements of the sequence are approaching to the limit. So we want to prove that eventually this sequence is bounded. So we know that the elements of the sequence starting from some place will be as close as the limit as we please. So for example, we could have them to be as close to the limit, no more than the distance of 1. So as we see here, all the elements starting from some place, perhaps somewhere here, their distance from the limit is going to be no more than 1. And so they're going to be contained in the ball of radius 1 around, or an open interval of radius 1 around the limit, which in this case is 0.6. And what about the rest of them? Well, about the rest of them, there's finitely many of them, right? All the elements starting from this point is inside this interval, which is of radius 1. So their distance from the limit is fixed. It's not more than 1. And outside of those lines, there are only finitely many elements, and so there will be the maximal element or maximal distance from the limit. And then we will see that all the elements of the sequence, their distance from the limit is no more than some fixed number. So for example, in this case, if we were to take all the elements of the sequence and project them to the y-axis, yeah, those are all the points projected. And now if we were to remove those, and then we actually see that all those elements of the sequence are within the symmetric interval around the 0 of, for example, size 15. So they're all from minus 15 to 15. So it's this open ball of radius 15 that contains all the elements. And that's a typical situation. We're going to prove that every convergent sequence has to be bounded. And so hopefully what we've seen here will set us an intuition for the proof, because starting from some point, their distance from the limit is going to be no more than 1, and outside of this interval, there is going to be only finitely many elements. So let's now give a proof for that. Now that we have the intuition, let us give a formal proof for that. And so let's recall the definition of a limit. Suppose that we have a sequence of real numbers that converges to the limit L. This means that for every epsilon, there exists a natural number n of epsilon such that for every n that is greater than n of epsilon, that is starting from some place, all the elements of the sequence will have distance from the limit that is smaller than epsilon. And note that this is for every epsilon. In particular, if we were to choose arbitrarily epsilon to be 1, it doesn't really matter, right? There would be a number n1 such that starting for every n that is greater than n1, this inequality holds. So let's see. So in particular, if we choose epsilon equal to 1, there exists a natural number n1 such that a n minus l absolute value is no bigger than 1. Now, what we have here is this other side of the triangle inequality. And this simplifies things for us. And this holds for every n that is greater than n1. So in particular, this means that a n, the absolute value of a n minus the absolute value of l, is smaller than 1. And this is all we need. The other part says that this is bigger than minus 1. But it's enough actually to know that this is smaller than 1 to conclude that for every n that is greater than n1, the absolute value of a n is no bigger than this constant fixed number, which is the limit, the absolute value of the limit plus 1. So this means that for every n greater than n1, the absolute value of a n is no more than this. And about the rest of them, so now we have this finite set of all the elements that may not satisfy this condition, right? So we look at this set of absolute values. It's a finite set, therefore it has a maximal element. So let's let m be this maximal element. And so for every I that is between 1 to n1, we have that ai is no more than m. And now every element, so if we now define m prime to be the maximum of m and l1 plus 1, then every element of the sequence is smaller or equal than m prime, which means that we have proved that the sequence is bounded. Okay, so if we were to do the same thing for metric spaces, the proof goes unchanged. So let xd be a metric space that every convergent sequence in xn is bounded. And so suppose that the sequence an in a metric spaces converges to a point x0, then the proof is basically the same. This means that for every epsilon there exists n of epsilon, such that for every n greater than n of epsilon holds that the distance of an from x0 is epsilon. And in the case of real numbers, this distance function is replaced by the absolute value of a n minus x0. So if something seems too abstract, just think of it for the real case, for the real numbers, and it's just the same. So it's all about the distance here. And now it's exactly the same. If we in particular choose epsilon to be 1, then there exists natural number n1 such that the distance of a n from x0 is no more than 1. And this holds for every n greater than n1. And now if we consider this finite set, then of all the distances of elements from a1 up to a n1 from the point x0, it's a finite set, right? So a finite set has a maximal element. And so let m be the maximal element, and then for every I, the distance of ai from x0 is no more than m, and then it's just very similar. Now if we define r as this radius of the ball that will contain all the elements of the sequence to be the maximum of m and l, absolute value of l plus 1, then what we have is that the distance of every sequence element from x0 is no bigger than this fixed number r, which proves that the sequence is bounded. So in every metric space, every convergent sequence has to be bounded.